Assalamu alaikum everybody. Welcome to our 7th lecture for the course Introduction to Artificial Intelligence. This lecture is titled Quantifying Uncertainty. And here is the outline. Acting under uncertainty. So first we discuss as a motivation how an agent should behave rationally under uncertainty situation. Obviously this involves some kind of probability. So we study the basic probability notations that we need as a background in order to develop agents that can act under these uncertainty situations. Some of these basic notations include probability axioms, unconditional probability, conditional probability, random variables, probability distribution, and finally joint probability distribution. Having studied these basic probability notations, we will then look at how to do inference using full joint distribution. We study the notion of independence when two events or two propositions are independent. And finally, we look at the Bayes rules and its use. So let's get started. Acting under uncertainty. We recall that when we studied searching, generally we viewed actions as deterministic. In other words, if you are in a state S1 and you execute a certain action A, you arrive at a state S2. There was also a fixed initial state S0. So with these deterministic actions and a fixed initial state, it follows that after executing any sequence of actions, we know exactly what state we shall arrive at. However, in partially observable environments, we might not know the exact start state. We might not even know which state we are in at any particular time. For example, in a poker game, you don't know what cards your opponent has. Similarly, in non-deterministic environment, which are called stochastic environment, we might not know all the effects of an action. As we recall, in deterministic environment, we know if we take an action exactly where we are going to be. But in stochastic environment, we don't. So, as shown in this diagram, in fully observable environment, which are also deterministic, like the searching environment that we have seen before, there is a clear certainty of the state we are going to arrive at after you execute a certain action. But in environments that are partially observable or fully observable but stochastic, there are elements of uncertainty. For example, when you roll a die, we don't know exactly what we're going to get. Is it a 1, a 2, a 3, a 4, a 5, or a 6? We don't know. Also, when we drive a car down a road, we don't know exactly the status of the road. There may be some accident there that is creating a traffic holdup, and so on. So the question is, how should an agent act rationally in this uncertainty situation? And the answer is not straightforward actually. It involves probability, and also utility theory. Let's take an example. So consider the problem of going to the airport by taxi. Obviously, this may involve a number of uncertainties, including the following: partial observability. We don't know the exact state of the road. We don't know how other drivers are going to behave on the road, and so on and so forth. Similarly, the actions are stochastic. All right, you may have a flat tire at any particular time. There may be some accidents that will create traffic holdup. There also may be noisy sensors, for example, inaccurate traffic report, and so on. Now, let us define an action AT to mean the action of leaving for the airport T minutes before the flight. And suppose we have the following possibilities of reaching the airport on time based on the corresponding actions. So we have A25, meaning leaving for the airport 25 minutes before the flight. Obviously, the probability of reaching the airport on time, if you take this action, is very small, 0.04. We have A90, which is much better, probability of 70%. A120, if you leave 2 hours before the flight, you are guaranteed to meet the flight by 95%. And the last one, A1440. So this is like 24 hours before the flight. So this guarantees almost 100% that you will catch the flight. The question is, which of these actions should our rational agent take? As I said, the answer is really not straightforward. It depends on the agent's preferences for missing the flight versus the time spent waiting at the airport for the flight, and maybe other preferences as well. In other words, a rational agent, before it takes an action, must consider the relative importance of the sub-goals involved. Alright, so there may be more than one goal in this case. Obviously, meeting the flight is one goal, but also the agent may not want to spend too much time waiting at the airport. So that is another goal to consider, and so on. The study of relative importance of sub-goals is actually covered by what is called utility theory, which we shall not cover in this lecture or in this course particularly, but it is important. The other aspect is the degree of belief that the sub-goal will be achieved, and this is based on probability theory. Now, probability theory is basically the subject of this particular lecture. Okay, so as you can see, the agent, for it to determine which action to take, it needs the notion of decision theory, which consists of two components, probability theory and utility theory. As I said, we shall study probability theory in this lecture, but we may not be able to study utility theory. But the main thing we should know about decision theory, it says here, the fundamental idea of decision theory is that an agent is considered to be rational if and only if it chooses the action that yields the highest expected utility, average over all possible outcomes of the action. All right. Now, for the rest of this lecture, we're going to concentrate on probability theory, which will go a long way in helping us to decide how our agent should behave in this uncertainty situation. So, basic probability notations. Now, like logical assertions that we studied in the last lecture about knowledge representation, probabilistic assertions are also about possible worlds. However, whereas logical expressions say which possible worlds are to be strictly ruled out, those that are false, and which ones are to be accepted, those that are true, probabilistic assertions talk about how probable the various worlds are. All right. So in probability theory, the set of all possible worlds is called the sample space, omega. And a particular world among those possible worlds is denoted as small omega. The possible worlds are mutually exclusive and also exhaustive, meaning that two possible worlds cannot both be the case. So only one world can be true at a time. And similarly, there must be at least one that is true. Okay, so this exhaustive is also sometimes called complete. So one possible world must be the case. So for example, if we roll two distinguishable dice, then there are 36 possible worlds to consider, as we see in the next slide. These are the possible worlds that you may have when you roll two dice, two distinguishable dice at a time. So we have here a red and a blue die. A fully specified probability model associates a numerical probability P of W with each possible world. All right. So for example, each of the possible worlds we have in this particular case has a probability of 1 out of 36, because there are 36 possible worlds, so the probability of any one of them occurring is 1 out of 36. Now let's talk about some basic probability axioms that we should all be familiar with. The first one is that the probability of an event or of a world, a possible world, must be between 0 and 1. It can never be negative, and it can never go beyond 1. It is always between 0 and 1. This is axiom number 1. The second axiom, of course, is that when you add these probabilities, the probabilities of all the possible worlds in your sample space, they should add up to 1. So if you add all the probabilities of these 36 worlds, each one of them is 1 over 36, obviously you're going to end up with 1. Another important axiom is called inclusion-exclusion axiom. It says that if you have two events, A and B, then the probability of any one of them occurring, probability of A or B, is the same as probability of A plus probability of B minus the probability of both of them occurring at the same time. Okay, so the idea, if you look at this diagram, is that we are trying to find the probability of one of these events, A and B, occurring. All right, So if you look at it in terms of this Venn diagram, this is the probability of A happening, and this is the probability of B happening. If you add this up directly, you will see that you are adding the probability of this intersection twice. And therefore, to find the probability of A or B, you need to discount one of those intersections. So this is why we are saying minus probability of A intersection B. Probabilistic assertions and queries are not usually about particular possible worlds, but about a set of them, a set of possible worlds. For example, we might be interested in the cases where 2 dice add up to 11, or the cases where doubles are rolled out. So double here means having a 1 1, 2 2, 3 3, 4 4, or 6 6. In probability theory, these sets are called events, and in AI the sets are always described by propositions in a formal language. For each proposition, the corresponding set contains just those possible worlds for which the proposition holds. So the probability associated with a proposition is defined to be the sum of the probabilities of those worlds in which that proposition holds. And this gives us our second equation. It says for any proposition phi, the probability of phi is the sum of all probabilities omega which belong to our phi. Okay, so just add up all the probabilities and you will have the probability of that proposition. Add the probability of each element in that set, or which hold true for that proposition, and you will have the probability of the proposition itself. Now, the basic axioms of probability, particularly equation 1 and equation 2, imply certain relationships among the degree of belief that can be accorded to logically related propositions. For example, we can derive the familiar relationship between the probability of a proposition and the probability of its negation, as shown by this. Okay, so probability of not A, obviously by equation 2 that we just saw in the last slide, will be the sum of all the probabilities of the world for which not A is true. So add all the probabilities of the possible worlds belonging to or that satisfy not A. Now suppose we add to this the probability of A, and then we also subtract the same thing. Obviously we are not adding anything because this minus this will be 0. Now if you add the sum of the probabilities of not A plus probability of A, basically you are adding the probabilities of all the possible worlds in your sample space. So that is represented by this probability of all the worlds in your sample space omega. And this we know from equation 1 to be equal to 1. Okay, so you can see that basically, and this of course is probability of A. And therefore you have 1 minus probability of A as expected. So probability of not A is the same as 1 minus probability of A. So just based on equation 1 and equation 2, we are able to derive the relationship between probability of not A and probability of A. So let's take an example. Suppose we want to find the probability of getting a sum of 11 when we roll 2 dice. Obviously, there are 2 cases where this can happen, where the first die is a 5 and the second one is a 6, or the first one is a 6 and the second one is a 5. In both cases, if you add, you're going to get 11. So there are 2 possible worlds for which our proposition will be true, and therefore the probability of total equal to 11 will be the sum of the probabilities of these 2 possible worlds. So probability of 5 and a 6 plus probability of 6 and a 5, both of which are 1 over 36. So when you add them up, you're going to get 1 over 18. Now probabilities such as P total equal to 11, or probability of getting a double, are called unconditional probabilities, sometimes called prior probabilities, or simply priors. So this type of probabilities refers to degrees of belief in propositions in the absence of any other information. This is where the term prior comes. Before we have any other information, what is the probability? So it is called unconditional probability. However, most of the time, we have some information, usually called evidence. So we have some evidence that has already been revealed. For example, the first die may already be showing a 6, and we are waiting for the second one to stop spinning so that we see what it will show up. So in this case, we are interested in the conditional probability, or posterior probability, or simply posterior of rolling doubles, given that the first die is a 6. This type of probability is written as this: P of doubles given die 1 is a 6. Okay, where the bar here is normally pronounced as given. So probability of double given the first die is equal to 6. And clearly, in this case, probability of doubles given the first die is a 6 is going to be 1 out of 6, because there are only 6 possible worlds where the first die is a 6. And of those possible worlds, only one of them we will also have the second die to be a 6. So the probability of doubles, given that the first die is a 6, is actually 1 out of 6. Mathematically, conditional probabilities are defined in terms of unconditional probabilities. And this is the definition. For any proposition A and B, we have probability of A given B is the same as probability of A and B divided by probability of B, which will hold, of course, as long as probability of B is greater than 0. For example, probability of doubles given that die 1 is equal to 6 is the same as probability of both double and die 1 equal to 6 divided by probability of die 1 equal to 6. So obviously the probability of doubles and die 1 equal to 6 is going to be 1 over 36. If you look at our possible worlds, there's only one possibility where we have both a double and die 1 is a 6. This is the only particular case where we have 6, 6. So the unconditional probability of that is 1 over 36. Alright, so that's going to be 1 over 36 divided by the probability of die 1 being a 6. The probability of die 1 being a 6 is of course 1 over 6, because there are only 6 walls in that case, and only one of them will give us a 6. So what is 1 over 36 divided by 1 over 6 is clearly 1 over 36 times 6 over 1, and if you do the math, you see that it's going to be 1 over 6. So the probability of doubles, given that die 1 is a 6, is actually 1 over 6. The definition of conditional probability, equation 3, can be written in a different form, which is called product rule. And it is basically by multiplying both sides of the equation with probability of B. So you will have probability of A and B to be equal to the probability of A given B times the probability of B. You can also write it in the form probability of A and B equal probability of B given A times probability of A. So this are called the product rule. Probability of A and B is probability of A given B times probability of B, which can also be represented as probability of B given A times probability of A. Alright, let's move on to random variables. Propositions are written in a notation that combines elements of propositional logic and constraint satisfaction notation. This is a factored representation in which a possible world is represented by a set of variable value pairs. Variables in probability theory are called random variables, and their names begin with an uppercase letter. Thus, in the die example, total and die 1 are example of random variables. Now, every random variable has a domain. For example, total will have a domain from 2 to 12. Obviously, the minimum value you can have is 2, where each die is a 1. For die 1 random variable, however, the domain is 1 to 6. We could have Boolean random variables. In that case, the domain is only containing 2 values, true or false. Notice that the true or false are written in lowercase letters. So the variables themselves will start with capital letters, but the values are always in small letters. The proposition that doubles are rolled is written as doubles equal to true. Now, by convention, proposition of the form A equal to true are abbreviated simply as A. So if we just say A, is the same as saying A is equal to true. Whereas A equal to false is abbreviated as not A. Now, as in CSPs, Domains can be set of arbitrary tokens. So for example, domain for a random variable age can be baby, teen, adult, and the domain for weather might be sunny, rain, cloudy, and snow. When there is no ambiguity, it is common to use a value by itself to stand for the proposition that the variable has that value. So if we just say sunny, it should be interpreted to mean weather is equal to sunny. Variables can also have infinite domains, and they can also be discrete or continuous. So we could have, for example, integer values or real numbers. For any variable with an ordered domain, inequalities are also allowed. So for example, we could have a random variable, number of atoms in the universe is greater or equal to 10 to the power 70. Finally, propositions can be combined by using the connectives of propositional logic that we discussed before. Example, the probability that the patient has cavity, given that he is a teenager with no toothache, is 0.1, can be represented as follows. So probability of cavity given no toothache and teen is equal to 0.1. Alright, let's move on to probability distributions. Sometimes we will want to talk about the probabilities of all the possible values of a random variable. Okay, so we could write something like this. Probability of weather equal to sunny is 0.6, weather equal to rain is 0.1, cloudy is 0.29, and probability of snow is 0.01. Now, instead of doing it like this, we normally abbreviate using something like a vector. We normally abbreviate it like this. We say P of weather, and notice that P here is capital P. So P of weather with capital P means the probability of all possible values of weather, and is normally represented as a vector like this. So you list the possible values, or you sometimes write it as a table where you provide the values of each of the probabilities of each possible world. Alright, so as I said, where the bold P indicates that the result is a vector of numbers, and where we assume a predefined ordering. Okay, so here the ordering is assumed to be the first value is sunny, second one is for rain, third one is for cloudy, and the last one is for snow. We say that the P statement defines a probability distribution for the random variable weather. Note that we must have each probability to be greater or equal to 0, and when you add them all together, we should have a 1. So if you add up the values in the probability distribution, they should all add up to 1. Now we can also have joint probability distribution. The P notation can be used for distribution on multiple variables, multiple random variables. In that case, it is called joint distribution. and this is how you represent it. So you still use the capital P, and in bracket you specify the variables involved. So P weather, comma, cavity denotes the probabilities of all combinations of the values of weather and cavity. This is normally also represented as a table where you have the possible worlds for one of the probability on one side and the other one on the other side. Of course, there can be more than two variables, so in that case there may be more columns to indicate the other variables. Now we can also mix variables with a value, as in the case of P of sunny, comma, cavity. So this is going to be a two-element vector given the probabilities of sunny day with a cavity and sunny day with no cavity. So the two possible values for cavities will be there, but the sunny will remain fixed. The P notation makes certain expressions much more concise than they might otherwise be. For example, the product rule for all possible values of weather and cavity can be written as a single equation. So P of weather cavity equal to probability of weather given cavity times probability of cavity. Obviously, this is a short way of writing the 8 equations involved. If you are to write it in the normal way, there will have been 8 possible equations where we associate the different values for weather and the different values for cavity. So for example, you could have probability of sunny given cavity, probability of sunny with no cavity, probability of rain with cavity, probability of rain, no cavity, and so on. So instead of having these 8 different equations, we can simply write it as this single equation. So much more concise. Right, now so far we have defined a syntax for propositions and probability assertions. We have also defined part of the semantics, particularly equation 2 defines the probability of a proposition as the sum of the probabilities of the worlds in which that proposition holds. Now to complete the semantics, we need to define what the worlds are and how to define if a proposition holds in a world. Now, a possible world is defined to be an assignment of values to all of the random variables under consideration for that particular world. Clearly, this definition satisfies the basic requirement that possible worlds must be mutually exclusive and exhaustive. All right. Example, if the random variables are temperature, shortened as T, with possible values as hot and cold, and weather, shortened here as W, with possible values sunny, rain, cloudy, and snow, then there are 2 times 4 possible worlds involved. Essentially a 2D table where you have the possible values for the weather on one side and the possible values of the temperature on the other side. It follows from the definition in the last slide that the probability model is completely determined by the joint distribution of all the random variables, meaning the full joint probability distribution. For example, for the temperature and weather example we just mentioned, that fully joint distribution can be represented as a table like this.